Alpha halogenation is one technique we can use to functionalize the alpha carbon. As you might expect, we end up with a halogen at that position. So we can use H3O plus catalyst, which means we don't need a lot of acid, but we do need the acid to get the reaction started. And then we can use bromine or chlorine, or I believe iodine can also work. And we end up with replacing one of the alpha hydrogens with the halogen that we're working on. And then of course we make HBr in this case as the byproduct. So how does this work? Well, the first thing to do is to react our ketone with acid, just like we saw in the previous video. This is sort of the acid catalyzed enol formation, and that's what we're going to do now. So we'll protonate that, then we'll use water to remove the alpha hydrogen, just like we saw before. And really I should be using equilibrium arrows here, because when we're using acid catalyst, as we saw in the aldehyde and ketone chapter, mechanisms and reactions can go in both directions almost all the time with these acid catalyzed with lots of proton transfers. So I should be using equilibrium arrows. I'll try to remember that. Now I have my enol. Remember that we discussed the enol being nucleophilic at this carbon based on dropping the lone pair from the O down to reform the double bond. So let's do that and attack the bromine as the electrophile. And with bromine molecule has a good leaving group in the form of bromide, and that gets us to this situation where we basically have a protonated alpha bromo ketone in this case. And one more step, I can use bromide, or probably better to use water to regenerate my acid. Water's a little better of a base than the bromide is, but that's how we're going to basically put on an alpha halogen. We could look at a couple other options. If we have a ring, or maybe not necessarily a ring, but an unsymmetrical ketone, such as this one, and we subject it to H3O plus and Br2, we're going to get a couple of options, some Regio Isomers. Bromine could go on either side, and as you might guess, there is a favored side. This is the major product, and that's because you can see how that enol versus this enol. This enol is basically a tetra-substituted alkene, whereas this enol is a tri-substituted alkene. So this is the more stable intermediate that's going to form fastest under our acid-catalyzed conditions with this unsymmetrical ketone. So since this is the major product, when this reacts with bromine, we end up with a bromine at this tertiary position way more often than we end up with a bromine at the less substituted position. So that's how we're going to distinguish the major and minor products. Another cool thing we can do with this reaction is add some pyridine. It's a non-nucleophilic aromatic base, and we can remove what we call the beta hydrogen relative to the leaving group and produce a ketone here, or I'm sorry, an unsaturated ketone. We call this an alpha, comma, beta unsaturated ketone. And these have some high utility. You can see that we've produced a dienophile now, if we wanted to. We could now form our own dienophile. But this allows us to install some functionality next to the ketone that we can then play with in further reactions. So let's look at what happens when we react a carboxylic acid with alpha halogenation, and that results in the Hell-Volhard-Zelinsky reaction, a very interesting name. So we're going to take carboxylic acid, we're going to react that with bromine and PBr3. We saw PBr3 back in the alcohol chapter when we used it to form alkyl bromides from alcohols. And so now we're going to essentially use it for a similar process. It's going to help us turn this OH temporarily into a bromide. So that's the first step. Second step is water workup. And we're actually going to end up with an alpha bromo carboxylic acid. So How does that work? Well, the PBr3, through a mechanism we're not going to get into, makes this acid bromide. And this is more reactive. So it will equilibrate with the enol form more easily. And that allows us to react the enol with Br2 through the same mechanism we saw on the previous slide. That gives us this alpha bromo acid bromide. And via water workup, we're basically going to substitute the bromide for OH. And then we end up with the alpha bromo carboxylic acid. And so we can, I think, do this primarily just with bromine. So we can install a alpha bromine on a carboxylic acid. And then we can do other chemistry with this alpha bromine too if we want to. We now have an alkyl halide that we can play with. Another reaction is the Haloform reaction. And it also involves alpha bromination, this time using base. Let me draw sodium hydroxide here and some bromine. And the end product is the alpha bromide. So we can remove, just like we saw with the enolate formation under base catalyzed conditions, we can remove the alpha hydrogen, making this resonance stabilized enolate. Again, this supports the idea that the alpha hydrogen is more acidic than simply a beta or gamma hydrogen. And this enolate can react with bromine to kick off bromide, and I believe that will directly produce this alpha bromo ketone. The interesting thing about this is the bromine causes the ketone to be more reactive. So it's harder to stop at this single bromine. There is another alpha halogen at that position, so most likely we would get two bromines there. So this is going to be the end product. It's hard to stop at the monobromination product. So typically on a standard ketone like this, it's kind of, maybe it's useful to have two bromines here, but most of the time we probably just want one, so we can do some interesting chemistry with that. But it can be a useful reaction if we have a methyl ketone. So let me draw that. So let's say I have a methyl ketone, and in this case I want to have no alpha hydrogens on the other side. So what's going to happen here is that we mix it with NaOH, Br2, and really it's going to be excess of both of these. What we're going to get is loss of that methyl carbon, and it's going to appear in the form of bromoform. You've heard of chloroform. That's just HCCl3. This one is HCBr3. That's bromoform. How does that work? Let's look at this a little more carefully. We just saw the base not the base catalyzed, but the basic alpha halogenation. And so that can happen several times, and we can get this situation if we do it 3 times on the methyl group. And so now this is actually a decent leaving group because it would make an anion that's stabilized by induction. So we're actually going to attack the carbonyl carbon in a nucleophilic attack. And then we're going to lose CBr3 anion. And you can see that this is kind of strange looking. We don't often lose carbon anions, but this is stabilized by induction. Each CBr bond is strongly polar, and it helps to spread out that negative charge. Also, as soon as this CBr3 anion is formed, it is in close proximity to this newly formed strong acid. And so we can immediately deprotonate to make the carboxylate and bromoform. So this CBr3 anion does not stick around very long. And then the second step here would be mild acid workup, so that we can get back to our carboxylic acid neutral species. And so you can obviously draw the proton transfer mechanism here, where I just take some acid, protonate this O, and make the carboxylic acid. So now we have the ability to take any methyl ketone that doesn't have alpha hydrogens on the other side, basically cleave that CC bond, and end up with a carboxylic acid. So now we have a way to take a methyl ketone and turn it into a carboxylic acid, which can be very useful synthetically. And we'll see that more later on in this chapter as we talk about synthetic utility of these problems.